Hello, this is going to be a little bit of a review for the first exam in 243, and I'm just going to go through the book and do some of the problems. So doing this on your own is, just as good as watching me do it, but it seems like people sometimes like, to have a little review session where somebody goes through and uh, you can have somebody to do the problems with. I'm only a recording, but I'll do the best that I can. And as I do these, I suggest that you maybe pause the video and try to do them yourself instead of just watching me do the solution. You'll get a lot more out of it that way. Also, in case you're having a hard time seeing anything, if you're watching this video on YouTube, there's a little gear or sprocket symbol down in the bottom right that lets you adjust the video resolution. And if you put that on HD, it might help you see some of this text. So let's just start with the first section, and I guess, first things first, let's just plot some points in the in three-dimensional space. So let's look at number 2 there. So I guess a lot of people will find this kind of easy, but don't want to presume anything. So let's say that's the z-axis, that's the x-axis, and that's the y-axis. And let's plot the point 0, 5, 2. So that means 0 far out on this is the x-axis, this is the y-axis, this is the z-axis. And 0, 5, 2 would be 0 out on x, and 1, 2, 3, 4, 5 on the y, and 2 up in the z. 1, 2. So here's this point. Yeah. So it's 0 out in the x direction, and it is 5 out in the y direction, and 2. Yeah, I've already said that, I think. So let me now undo all this, just so I don't want this to interfere with my my picture for the next point, which is, you know what, I'm going to skip 4. I don't like 0 because 0 seems too special. So let's look at 2, 4, 6. So that's 1, 2 out in the x direction, and then 1, 2, 3, 4 out in the y direction, and 6 up in the z direction. 1, 2, 3, 4, 5, 6. And so sometimes to draw the picture, if you just draw a point in three-dimensional space, it can be kind of ambiguous. It could be sort of many places in three-dimensional space, and the picture would still look the same. So I think the best thing you can do if you really want to indicate where the point is to draw a little box like this. And just the meaning of the coordinate system is that this side of the box is the y length, and that in this case is 4, and this is the z length, which is 6, and this is the x length, which is 2. And here you have this little point. Okay. So plotting points in 3D I don't think ever was very hard, so I'm just going to stop there and go on and look at something else. What about number 4? Yeah, this is going to take a while, huh? This actually works surprisingly well. Okay. So, oh, except Z got lost. You know what I'm going to do? I'm just going to copy this so that I can paste it the next time I want it. And so projections. We didn't talk about that too much in class, but it's important. So let's do a couple of these projection problems. So what are the projections of the point 2, 3, 5 on the basic planes? So the xy plane, the yz plane, and the xz plane. So if nothing else, doing this problem will define what the x, y, yz, and xz planes are, which is pretty basic terminology that everybody should know. So first let me plot the point. So the point is 2, 3, 5 here. So 1, 2, 1, 2, 3, 1, 2, 3, 4, 5. So let me sort of draw the best picture I can here. Okay. And seems like this point is going to be plotted somewhere like right there. So let's say that's the point. and we're going to look at its projection on the various planes. And so let's just do them one at a time here. So what's the projection of this point on the xy plane? So this, it's kind of hard to indicate what I'm talking about, but like the floor of the room, if you imagine that this is a room, is the xy plane. And the projection of this point down here just means forgetting about the z coordinate. So the projection is 2, 3, 0. So that's 2, 3, 0. It's hard to read because the color is so weird. And so now let's do the projection onto the yz plane. So the yz plane is like the back wall of the room, and this would be the projection. And so to plot that point, you're just forgetting about the x coordinate. Notice that you're forgetting about the coordinate that's not mentioned in the name of the plane. So x is not mentioned in the yz plane. That's the coordinate that you're forgetting. So it's 0 and 3 and 5. And the projection on the xz plane, so the xz plane is like the left side of the room here. You forget about the y coordinate and it becomes 2, 0, 5. Okay, so those are the projections. My wife is cackling upstairs. I've also had just an incredible amount of coffee, so my hand is even more jittery than usual. I feel like Bob Schultz at drawing Snoopy at age 88 or something. So let's do a couple more of these. So I'll go down, and this was my plan to be able to paste this, and it works pretty well. I'm proud of myself. Oh look, I can even change the colors. Okay, don't even really want to change the colors, but so number 5 says, describe and sketch the surface in R3 represented by the equation x plus y equals 2. So let's see. So, you know, frequently with these three-dimensional things, it's honestly hard to think in 3 dimensions. So even great mathematicians admit this, like Stephen Hawking says that he finds it hard to think in 3 dimensions, and that should tell you something because he's a famous mathematician. Let's look first of all at what x plus y equals 2 looks like in the xy plane. So this is sort of an overhead view of the xy plane. So there's x and there's y, and everybody knows that this is just a line. And so if you move x over to the left, you'll see that it's a line with slope -1 and y-intercept 2. And the slope is -1, so this is also 2 here. And so it would be just a line like this, right? So if I draw that line as best as I can down here in 3-dimensional space, there's 1, 2 on the x-axis, 1, 2 on the y-axis, and here's my sort of line that is in the, I mean for this line to be completely contained in the xy plane. Whoa! Now what makes this different from just a 2-dimensional graph is, whoa! Sorry, my big fat hand is dragging on the pad and causing all kinds of problems. And now I'm going to get sued for copyright violation. I don't even know which direction I went. Here we are. Where was I before? 200. Now in the equation x plus y equals 2, there's no mention of the z-coordinate. And that makes the z-coordinate angry. And what he does in retaliation is, it just makes, you know, now for all z values, you've got infinitely many points on this line that satisfy the equation, I mean the line in the xy plane, but also just putting in any z-coordinate also makes the relationship true because z doesn't even appear in the stupid equation. And so what you get is, I hope you see this the way I do, as sort of a vertical plane in 3-dimensional space. The line just extends up and down forever because any z-coordinate also works. And so what this thing describes is a vertical plane, and it's that vertical plane. So I think that's a pretty good description of it. So I'm going to consider that problem solved. So what else should we do here? So number 15 and 16 and 17, these are all about completing the square. So I guess we didn't really go over this in class. Sometimes I think things are obvious that might not be obvious, but just like the standard form of now I'm really self-conscious about my fat hand causing problems. Just like in two-dimensional space, you know, if you do x minus h squared plus y minus k squared equals r squared, then this gives you a circle of radius r centered at h comma k. And the three-dimensional analog of that is a sphere, and the basic form of a sphere is x minus h squared plus y minus k squared plus, now I've got to pick a weird letter, z minus, geez, should have thought of this beforehand, h, I, j, k, l, how about l, squared equals r squared. So this is a sphere centered at h, k, l that has radius r. And what you have to do in, say, like number 15 is just to complete the square. And you may not have completed the square in a while, but you can read the Wikipedia article, and if you made it to Calculus 3, I'm sure you'll have no trouble doing the completion of the square algorithm. Once you do the completion of the square technique on number 15, it's easy to put it in the standard form, and that's basically what they're asking you to do in 15 through 18 here. So what else have they got? Find the lengths of the sides of the triangle PQR. Is it a right triangle? Is it an isosceles triangle? Oh no, massive copyright violation. Kosh Snowflake, where are we? Where did we go? Oh my god, it's this thing. Did you know you can make this extend over the edge of the table? It's related to the harmonic series. Where are we? Oh god, we went so far. I'm going to pause this so I don't give away any of the textbook. And we're back, and that took absolutely no time for you, so I should not have even made any note of it. But a lot's changed for me. And so this question about is it a right triangle, one way to check to see if it's a right triangle is just to see if the lengths of the triangle satisfy the Pythagorean equation. So how can you do that? Let me get my three-dimensional axes back and scoot it down some. So I'm not going to plot these 3 points. We've already been over point plotting, and you can do that yourself. What I will do, though, is I want to plot the associated vectors PQ. I'm so self-conscious about my hand touching this really sensitive pad. And PR. And, you know, PQ is just Q minus P, PR is R minus P. So what are those things? PQ is going to be equal to, I'm going to write it, this is supposed to be a sharp bracket now. So 7 minus 3 is 4, 0 minus minus 2 is 2, 1 minus minus 3 is 4. Okay, so I will sort of plot that point. So that goes 1, 2, 3, 4. 1, 2. You know what's awesome is somebody counting in a monotone. And 3, 4. And so where does that go? It goes like right there. Okay, so here he is. So that's the vector PQ, and sort of coming out of the origin. That was a terrible line, sorry. Comes out of the origin like this, and it has that little barb on the end of it like vectors do. It's wearing lipstick now. And PR is, so with the little vector bar, that's just R minus P, and R minus P is 1 minus 3 is negative 2, 2 minus minus 2 is 4, 1 minus minus 3 is also 4, and so that's going to be, let's go back 2 in the x direction, over 4 in the y direction and up 4 in the z direction. And yeah, so you've got this point now, and let me make a little magenta vector for that. So here, remember this one with a lipstick on, that's PQ. This magenta one is PR. We want to know if these things form a right triangle. So how can we do that? So I'm going to compute 3 things. One thing is, God dang it. I'm seeing it as a triangle. Let me put in the third side here. Oh, that's lame. Maybe you're thinking just chill out. But I told you I had all that coffee, and it's very hot in this room, and I hear things clanging upstairs. Makes me, oh God, how many times can I do this? So now I have a triangle with a blue side, a green side, and a purple side. I'm going to compute the lengths of every single side. And this is just a good review of how to compute lengths like this, if nothing else. So what is the magnitude of PR? It's the square root of the sum of the squares here. So that's 4 plus 2 times 16 squared. What is 16 squared? 16 is 2 to the 4th. So if you square it, you get 2 to the 8th, which is 256. And then if you double that, you get 512. And then if you add 4 to 512, you get 516. It's 516. And what about PQ? PQ is going to be the square root of the sum of these squares. So again, that's going to be the 4s. What did I say that was? That's 2 times 16 squared. So that's 16 to the 2 to the 4th power, 2 to the 8th power, 256. Oh, it's exactly the same. Okay. And so what is the green side? So the green side is the magnitude of the difference between the two. It doesn't matter which way you go. So I'm going to go from PQ to PR here. I can't believe that I have enough dishes that they are just always being cleaned, but I guess I'm fortunate that my wife is nice enough to clean them. And so what is PQ minus PR? Let's see if I can just do it all in one shot. So the first coordinate of PQ is 4 minus negative 2 is going to be 6. So 6 squared plus 2 minus 4 is negative 2, squared is 4, plus 4 minus 4 is 0. So let's just not write that. So this is the square root of 40. Square root of 40. So now is it true that, which one of these is going to be the hypotenuse? I guess the longest side is the hypotenuse. But this triangle sort of looks like this. It's got a short side that is the square root of 40, and it's got 2 long sides, and both the long sides have length square root of 516. So square root of 516, square root of 516, and down here is the square root of 40. And this thing, I guess I could have stopped a long time ago. Maybe you're actually yelling at the screen and banging your fist right now. This is clearly an isosceles triangle, and there's no way that an isosceles triangle can be a right triangle, is there? Because it has to have a 90-degree angle. Yeah, I guess that it could. If there was a 90 degrees here, and then these two could be equal, right? But you couldn't have the right angle be one of the 2 sides that are equal, because if one of those was right, then the other one was right, and you wouldn't have a triangle, you'd have a box. So if any angle is right, it must be that angle, and so that means 40 must be the hypotenuse if it's a right triangle, but the hypotenuse is always the longest side, and so that's absurd. So the triangle is not right, and it is isosceles. And that's all I have to say about that. I'm going to pause this and close the door so it gets even hotter in here, but much quieter. Okay, so let's keep going a little bit. I just love these geometry problems. I guess in every section there are tons of geometry problems. So I'm like a pig at a trough right now. Number 9 and number 10 I think are important questions. Actually, all of these are pretty easy, but let's just look at number 9. Determine whether the points lie on a straight line. So let me just give you some advice on how to do that yourself, and let's not all do it together. But these are 3 points in space. Crap. 3-dimensional space. So, here's A, let's say here's B, and here's C. And how are you going to decide if these things all lie in the same line? What you have to do is look at the directions between them. So there's from A to B, and there's from B to C. So if these things all were on the same line, like A, B, C, like that, then if I found these two vectors, this is just A minus B, and this is just C minus B. Is that right? No, yeah, C minus B, and this is B minus A. I misspoke. The vector from A to B is B minus A. And so if they were all in the straight line, then these two vectors would be scalar multiples of each other. This would be some vector v, and this would be c times v for some constant. And you would be able to recognize that. And that's what you need to be looking for here. These two vectors are not going to be scalar multiples of each other because they go in different directions. So how about number 10? How could you do number 10? Find the distance from the point to each of the following projections. So we already have a picture of the projections. I don't think I deleted it. It's up here. Whoa. Yeah. So instead of using the given point, just use this as a picture of what the projections look like. If you want to find the distance from the point to these planes, you just need to find the lengths of these lines, and that's just a difference of vectors. Do you see? If this is going this way, then this is just that point minus that point. And so that gives you the vector whose magnitude is the same as the distance from the point to its projection onto, in this case, if it were really that point, it would be the projection onto the xz axis. And so you could do the distance to the xy plane similarly. And I think that's enough about that. Find an equation for the sphere, no thanks. This would just be setting up several equations and then solving a system of 3 equations and 3 unknowns or something like that. Do it, it's red. Usually you should do the red points, but oh God, oh my Lord. Sorry, just one sec. So we're almost done with 12.1. The only one of these problems that I really like is number 39. That's an excellent problem. So if you have 2 points and you look at all the points that are equidistant from them, actually maybe this is easier to do in 2 dimensions. If this were a 2-dimensional situation, hopefully you can see that the answer would be a line. In a 3-dimensional situation, the answer is going to be a plane. So just write down, using the Euclidean distance formula, this relationship that they're describing, and you should get the equation for a plane. And now that we know the equation for planes, I should actually maybe try to do it. Okay, I'm going to go whole hog here and commit. I'm committing to the problem. So let's just say that we have some generic point. I guess R is something we frequently use for generic points, so I'll use that, x, y, z. And what does it mean for, what's the distance between R and A? Well, that's, the magnitude of A minus R. And what is that? That's the magnitude of -1 minus x, 5 minus y, 3 minus z. And what is that? That's the square root of, sorry, I don't like that. It's the square root of 1 plus x squared. It's just easier to forget about those minus signs. plus 5 minus y squared plus 3 minus z squared. Okay. And so what's the distance between b and r? So the distance between b and r is the square root of, don't like that, sorry. Still don't like that, but I'm going to live with it. So let's do 6 minus x squared plus 2 minus y squared plus negative 2, I guess, minus z squared. So I hate it when both are negative, but I'm going to live with that too. So what are we supposed to do? The problem is saying that these two distances are supposed to be equal. So if we set them equal to each other, then we can forget about the square roots. So just square both sides. And what you get is 1 plus x squared is, plus 5 minus y squared is, plus 3 minus z squared is equal to 6 minus x squared plus 2 minus y squared plus negative 2 minus z squared. And what's going to happen if you multiply all this stuff out? On the left-hand side, you're going to get a bunch of linear terms. And then you're going to get plus x squared plus y squared plus z squared if you expand all those binomials. And you'll get something similar on the right-hand side, won't you? It'll be, a different kind of linear thing, but it'll be some linear part. That means, just constants and then the variables raised only to a power of 1. So all the variables in this part are raised to a power of either 0 or 1. And you'll get x squared plus y squared plus z squared. And then all these quadratic terms will cancel out. And then you'll get that some linear function of xyz equals some linear function of xyz. And you can combine those. So combined like terms, and what you'll get is something in the form ax plus by plus cz is equal to d. And what is that? It's a plane. And you probably had already realized that just intuitively that it would be a plane, but that is a mathematical argument, or a sketch of a mathematical argument, that it actually is a plane. And stop here. Okay, so let's pick up again in the next section. I guess we've already been talking about vectors. Maybe I wasn't supposed to be using that language, but I did. So this first question is sort of a conceptual question, and it's based on the definition of a vector. Do you remember what that is? So a vector is magnitude and direction. So which of A, B, C, and D here have both magnitude and direction? A has only magnitude, it's not a vector. B has magnitude and direction, it is a vector. C has magnitude and direction and is a vector, and D has only magnitude, and so it's not a vector. Excuse me. What's the relationship between the point and the vector? It's, I don't know, that's a philosophical question. Pass. Write each combination. So this is good. It's about the geometric meaning of vectors. So here, let's just look at A. Write each combination of vectors as a single vector. So this one is PQ, that's the line from P to Q, plus the line from Q to R. So what does that mean? That means if you do PQ and then you do QR, what do you get? You can see that the answer is PR. So going from P to Q, then from Q to R is the same as going from P to R. So the answer to A is PR, and the other ones work similarly. You definitely need to be able to do number 5, and it's similar. So what's the geometric meaning of u plus v? It's just the same as taking v and putting it on the end of u, like that, and then the answer is the vector that connects the base of u to the tip of v when it's put at the end of u. And like we've already been saying, and I think we should maybe do b. Some people might be having a hard time with this. This is really fundamental, the difference of vectors. My computer is kind of choppy. Sorry about that. I probably need to, I don't know, beat it with a sledgehammer or something. So to do b, number 5b, what you need to do is draw both vectors so that they originate from the same point. And you can translate these things around and stuff like that without essentially changing them, because vectors are direction and magnitude, and translating them around doesn't change the direction or the magnitude. Let's imagine that's v and that's u. And b here, u minus v, so that's something that originates at the tip of u and terminates at the tip of v. So this red vector is u minus v. And this is a way to get the direction between 2 points when you regard u as a point instead of a vector and v as a point instead of a vector. So you should understand vector addition and vector subtraction and what the geometric meanings are. And 6, you're getting into scalar multiplication stuff. And that's something that is also very fundamental and crucial to understand. So if you have a vector v, like this, so all scalar multiples of v go in the same direction. Oh, jeez. Sorry, I'm drawing just like an orangutan, like a drunk orangutan in a medical experiment. So let's say this is v, and I guess I can draw v with the ruler still on. V. Okay, so this red thing is v, and what are all the scalar multiples of v? They are vectors that go in the same direction but don't necessarily have the same magnitude. So if I stop here, this could be c times v. And since this makes v shorter, you would know that c is something that's less than 1, because it shortens v. And you can even make v go in sort of the opposite, quote-unquote, opposite direction. I'm not sure opposite is the appropriate term here, but let's just say the other way. Okay, so this would be some negative c times v. Maybe I should use a different, I'll call it c1. And v, where c1 is greater than 0. I just want the negative sign here to actually be efficacious. So what I mean is that the sign of the scalar here is negative. So what happens if you consider all the scalar multiples all together? What you get is a line that just sort of, goes in the direction of v. So L, we call this line L. One way to think of what L is, it is all scalar multiples of v. Okay, so that's important to understand. Now you've got your scalar multiplication, sums, differences, they're combining them together and getting kind of crazy. What else is going on here? Stupid choppy computer, I'm going to throw it in the river. Oh God, what's happened now? We're back in 12.1, hold on one sec. So 13 through 16, you should be able to do those. It's still asking you about the meaning of vector sum. You should definitely be able to do these. We've already done some problems about magnitude and even the magnitude of a difference. So these are hopefully, if you can't do them, then do them. Actually, maybe you should do them anyway. Something about math, sometimes you think you can do something, but you really can't. And you have to debug your understanding of something by trying to do it and maybe failing. Don't be confident that you can do it until you test whether you actually can. Find a unit vector that has the same direction as the given vector. This is two things that we have not talked about yet in 21 through 23. One is what the hell is a unit vector, and another one is that notation that they're using with I, J, and K and stuff. So that, to me, makes this problem worthwhile. So let's see if I can get my fat hand under control. Number 21, minus 3i. I don't know why I'm copying it, because it's just right there. Unit vector that has the same direction. So, I don't know, my brain, I guess, sort of a phenomenological, philosophical thing, but I just find it easier to understand when it's written like that. And so here's a vector. It goes -3 in the x direction and 7 in the y direction, so it looks something like that. And let's call it something. Let's call it v. And it has a magnitude, but the magnitude is probably not 1. Let's check and see what the magnitude is. -3, 7, and if they're being nice, maybe this will actually be a square under the radical here. Let's see, so 9 plus 49, it's going to be 58, which is not nice. Okay. Now, all right. So what I want is something that goes in the same direction as v, but has length 1. That's going to be the unit vector that they want. Find a unit. What is a unit vector? A unit vector is a vector of length 1. So this is going to be some special c times v, and what c is going to be is just 1 over the magnitude of v. So the unit vector that goes in the same direction of v, and this is true for any vector v, is just v divided by its own magnitude. And this is also called the norm of v. So if you normalize a vector, that terminology means that you just translate it into a unit vector. And in this particular case, the answer is -3 over the square root of 58 I plus 7 over the square root of 58 j, and that would be this guy. So it would be length 1 in the same direction as v. So that's how you do it, and that's what it means. Now let's find something else to do. If v lies in the first quadrant and makes an angle of pi over 3 with a positive x-axis. Okay, so number 25 is worthwhile. And let's draw a picture of what they're talking about. So I think it's too early to turn that off. So it says it makes an angle of pi over 3, so that's something like that. And so there's this angle, theta here equals pi over 3. And they say that the magnitude is, I don't know why I wrote that vertical bar there. So the magnitude is 4 if you regard this as a triangle. There's just going to be a refresher in basic trig. They want you to write it in component form. And the length of this side of the triangle is going to be the j component. And the length of the triangle and on this side is going to be the I component. And you just use trigonometry to find what each one of those are. So what is, sine theta is going to be the opposite side over 4. This is O for opposite. And so the opposite side, the j component here, is going to be O equals 4 times sine pi over 3, which is 4 times square root of 3 over 2. And so that's 2 times the square root of 3. And that's going to be the j component. Let's just write that as j comp. Okay. And so similarly, the adjacent side, which is the I component, is going to be 4 times cosine square root of 3 over 2. And that is just 2. And that is the I component. So finally, v can be written in terms of its component vectors as 2i plus 2 times the square root of 3j. point, and we're done with that problem. So what else have they got? I guess we have to do this child pulling a sled. Sorry, fat finger mistake. The child pulls a sled through the snow on a level path with a force of 50 newtons. So maybe the challenge here is just to set up the problem. So here's the horizon. The child pulls a sled through the snow on a level path with a force of 50 newtons. This is sort of the path of the sled is that green line, and this is the force vector exerted by the child. And we know that the magnitude of the force vector is 50 newtons, and we know that the angle that it makes with the sled is 38 degrees. Find the horizontal and vertical components of the force. And you know what? I am not going to do that, because that's exactly what we just did. This is the I component, this is the j component, and so you can compute those using trigonometry exactly the way we did in the previous problem. Okay, so number 27, a quarterback throws a football with an angle of elevation. It's exactly the same, not going to do it. Number 28, gonna do it. Actually, which one do you like more, 28 or 29? I guess number 28. So number 28 doesn't come with a nice story, but maybe you should make up a nice story so that we can just consider this doing a word problem of the same form. Somebody could say, there are two puppies that are pulling on a blanket that's wrapped around the newel of a stairwell, and puppy one pulls with 16 pounds of force, and maybe he's a dachshund, and the other puppy is a golden retriever, and he's a little bit bigger, and he pulls with 20 pounds of force, which is slightly more, and then the blanket makes these angles just because that's how the puppies are standing. And you want the resultant force and the angle it makes with the positive x-axis. So in terms of geometry, that's just going to be the sum of these two vectors. So geometrically, you can immediately see the answer is going to be some vector that's approximately right here would be the tip of it, because if you take this and put it on the end of the other one, you get approximately right there. If you want to actually compute what vector that is, then you have to do some work, because to add these two vectors, the easiest way to add them is to find out what their components are. I feel like I just did the problem. Okay, so I'm not going to write it all out because it takes forever, and this video is already long. It's going to get longer. So to do number 28, find the I component of this guy, find the I component of this guy, add them. That's the I component of the result. Similarly, find the j component of this guy, find the j component of this guy, which is going to be negative. Add them, and the net is going to be about this much. And when you do that, you'll have the answer. This kind of problem, you should try number 32. Actually, try number 33, because the answer is probably in the back of the book. It's a similar kind of thing. This is a different story, but it's going to be just two puppies pulling in opposite directions, and you need to add the component vectors. We did this one in class. It's a cute problem, but it's not worth putting on the exam as a test question. How about this? So number 41 is a good question. This is describing a sphere of radius 1 centered at this point. And I guess that's the answer. Can you see why that's true? The book uses this notation a lot. R is varying over all points, and R0 is fixed. And so what happens is this is describing all the varying points R that are distance 1 from a fixed point, R0. And what does that do? That creates a sphere in three-dimensional space. All right, so I'm done with this section, and I'm going to stop this video. That's enough.